these calculus videos, written and performed by me, Patty Leitner.
Part 4. Integrals. Section 5.3. The fundamental theorem of calculus and the definite integral.
Lesson 1. The fundamental theorem and definite integrals. Part 2.
We can actually make this process of finding the exact area under a curve even faster by developing a new symbol. So that's what I want to explain about next. So on the next page, you notice it's titled the definite integral. And you may remember that we've already talked about what was called the indefinite integral. We did that in that section 4.9, I think it was 4.9/5.4. So the indefinite integral symbol was a symbol that just looked like this. We had a function inside, such as x to the fourth dx, and that was a symbol that said find the set of all antiderivatives of x to the fourth. That's what's referred to as an indefinite integral. I'll talk about the names for these things at the bottom of this page. What we are now talking about is what's referred to as a definite integral. So it's really a different beast altogether, but it borrows some of the same notation that we used for indefinite integrals. So the idea is the following. When we found the exact area under square root of x from 0 to 8, we had to use two steps to do it, to apply the fundamental theorem. Remember, first we had to find an antiderivative, capital F of x, and then in a separate step we found capital F evaluated at b and subtracted capital F evaluated at a. So it took those two steps. What we like to do is to do it all in one step by creating a new symbol. So the exact area, that's what we were looking for, and we write this symbol. You notice it has an integral of x to the 1/2 dx. Remember that in our step 1, that was our first step, was to find the integral of x to the 1/2 dx, that we could find our capital F of x. So we borrow that symbol, the integral, the indefinite integral symbol, because we have to find an antiderivative of x to the 1/2. But we add these things at the bottom and the top of our integral sign. I put 0, that's my a value at the bottom, and it is called the lower limit of the definite integral. And I put 8 at the top, that's our b value, that's where our interval ended, and that's referred to as the upper limit of our definite integral. And so we sort of combine all our information in one new symbol, and that new symbol as a whole is referred to as a definite integral, versus this type that doesn't have a lower and upper limit, which is called an indefinite integral. Okay, let's see how this new notation works. What we do is we essentially do step 1 and step 2 all in one step. Okay, so I'm going to start by finding my antiderivative of x to the 1/2, just as we did in step 1 of the process that we did on the last couple of pages. So I begin by saying, oh, okay, I know how to find the antiderivatives of x to the 1/2. I use the power rule, add 1 to the 1/2, that gives me 3/2, the reciprocal in front, 2/3, just as we did in step 1 of the previous couple of pages. Remember that we could add any integration constant c onto this, but we always choose c equal to 0 because that is the simplest antiderivative. So here's my antiderivative, but remember the fundamental theorem said we have to take that capital F of x, evaluate it at 8, and then subtract the value at 0. So we indicate that this way by putting a vertical line. The vertical line tells me I've already found the antiderivative, but it reminds me that I'm going to have to evaluate that antiderivative at my b value, which is 8 in this case, and then subtract the value at my a value, which is 0 in this case. So we find the antiderivative. That's right here. We draw a vertical line with our upper limit at the top and our lower limit at the bottom, and that reminds us that we still have to evaluate this antiderivative at 8 and then subtract the value at 0. So that's what we do next. We say, oh, okay, so that's going to be equal to, I'm just going to draw a line here, so that's going to be equal to 2/3 I pop in the upper limit in place of x, 8 to the 3/2, and then I subtract, and now I'm going to pop in my lower limit in place of x, 2/3, 0 to the 3/2. So this is the step that we were doing on the second page, where we said then evaluate capital F of 8 minus capital F of 0. But you notice we're doing it all in one step. And so at that point you just say, oh, okay, what is 8 to the 3/2? That's the square root of 8 cubed, just like we did before. This will come out to be 0. And if you simplify all of this, I think we ended up getting 32 root 2 divided by 3 as a final answer. But this way, to find the exact area, all we have to do is this one line, and that's by developing this new symbol. Well, this new symbol has this name. It is called a definite integral, and I'll explain why in a moment. So this symbol would be read the definite integral of x to the 1/2 dx from 0 to 8, from a lower limit of 0 to an upper limit of 8. Okay, well, I just want to make a remark about the indefinite integral that we talked about back in section 4.9/5.4 and the definite integral that we've just defined right here, this new symbol. And the indefinite integrals that we used to look at, if I looked at the indefinite integral of x to the 1/2 dx, remember we got 2/3 x to the 3/2 plus c. That was our answer. It was the set of all antiderivatives of x to the 1/2. And I want to remind you that the type of answer that you get here are really functions. It's really an infinite number of functions because you could add any c value onto there, but these are functions. So notice that you end up getting a family of functions as an answer. So the answer to an indefinite integral problem is a set of functions. Now that's very different from the definite integral that we just did. Remember, our answer to this definite integral problem ended up being a number. And so what we just did was the definite integral from 0 to 8 of x to the 1/2 dx. We went through our whole business. We ended up with 32 root 2 over 3, and this is a number. It's not a function, it's a definite number. So the answers to these two different types of integrals are completely different. An indefinite integral has a family of functions as an answer, while a definite integral has a number as an answer. And I believe that's where these words come from. This is referred to as a definite integral because the answer you get is something definite. It's a number, 32 root 2 over 3. Whereas an indefinite integral could have lots and lots of values depending on the particular value of x that you choose, and of course also on the particular integration constant that you choose. But this answer to an indefinite integral is a function, and so in a sense that's indefinite until you've specified what value of x you want to plug into that function. And that's the reason for the word indefinite versus the definite integral, where you get some definite number as an answer. Okay, let's go ahead and look at the next page. So on the next page, I just want to kind of go over what we just did, but in a more general setting. So we kind of set up the whole definite integral from 0 to 8 of x to the 1/2 dx. Let's talk about that new symbol that we've created, the symbol for the definite integral, in more general terms. So I said we've developed this new symbol that looks like this. So for a general function, little f of x, we would write it this way. We write our little indefinite integral sign just like we had before, but now it becomes a definite integral because I've put on a lower limit in general of a and an upper limit in the general case of b. So this is an upper limit. And we would read this the definite integral from a to b of f of x dx, or sometimes we just say the integral from a to b of f of x dx, and we assume that the person will know it's a definite integral from the context, from the fact that the limits are there. And remember, what happens is we find an antiderivative of little f. Usually we choose the antiderivative with the integration constant c of 0. And when we find the antiderivative, we usually use a capital F of x to denote that. So I found an antiderivative of little f, calling that capital F. So I wrote down here antiderivative of little f. And we write this vertical bar. Now, as soon as you write this vertical bar, it means you're done integrating. You've found the antiderivative of little f. You're done with the indefinite integral. And remember that you put the lower limit at the bottom of this vertical bar and the upper limit at the top. That's just to remind you that you still have to plug those values in and do capital F of b minus capital F of a. So that reminds us that I'm going to take this antiderivative, capital F, I'm first going to evaluate it at this upper limit, b, and then I'm going to subtract the value of capital F, and I'm going to plug in this lower limit of a. So that's, this thing now is our general new notation for the definite integral of a function little f of x. Okay, well, this also simplifies the way we state our fundamental theorem. If you go back to our statement of the fundamental theorem, I'm going to go back a couple of pages to where we stated our magical fundamental theorem. Remember, it's kind of lengthy to write out the fundamental theorem. We said if you want this green area under this curve, little f of x, you have to find an antiderivative, capital F, and the exact area is capital F of b minus capital F of a. Well, now we could write that same information that we have over here by using our new symbol for a definite integral. So let's see what that becomes. I'll move this off to the left. Now I can say, well, if I want this exact area under my curve little f of x, all I have to do to get that exact area is this definite integral. It's the integral from a to b of little f of x dx. And we say it kind of all in one little statement. Because remember what we said right up here was that that is capital F of b minus capital F of a when you go through and compute what this new symbol means. So it's another way of writing it instead of having to spell all of this stuff out. A is f of b minus f of a, where capital F is an antiderivative. We get to write it all in one neat symbol, which we are calling a definite integral symbol. Okay, well, I just want to emphasize everything that we've talked about so far in this section. We talked about it in regards to that specific example of the area under y equals root x from 0 to 8. Let's talk about it in general terms. So remember from our previous section, 5.1, we said the exact area under a curve y equal f of x from a to b could be found by using a whole bunch of right-hand rectangles. We call that r sub n. That was dividing up that interval from a to b into n subintervals and creating n right-hand rectangles. Adding those all up, that gave us an estimate for the area under the curve, and when we allowed the number of rectangles to go to infinity, we got the exact area. So the exact area A under the curve is the limit as n goes to infinity of f of x1 delta x plus f of x2 delta x and so on up to fn, f of xn delta x. Well, we can also write that using our sigma notation. So we said that's exactly the same thing as limit as n goes to infinity of the sum I equals 1 up to n. And what has to go inside here? Well, all of these terms have the same pattern. The only thing that's different is the subscript on the x. So I can say f of xi delta x. So that is how we rewrote this long sum in a nice, neat notation using the sigma notation. But now we also know from what we wrote up here with the fundamental theorem, this exact area can also be given by this definite integral that we've just defined. So this exact area A can also be written as the definite integral from a to b of f of x dx. that's really by the fundamental theorem. We often abbreviate the fundamental theorem FTC, Fundamental Theorem of Calculus. So by the Fundamental Theorem of Calculus, this limit of this sum of f of xi delta x from I equal 1 to n can also be written as this definite integral. Well, I just mentioned this for two reasons. One reason is what we said before, that we now have this new, very much simpler way to figure out this impossible limit. Remember when we were looking at the root x example and we got that horrible limit in terms of n that we had to try to figure out? That was nearly impossible. Let's see if I can find that. That was this limit right here. So that was something that was, how are you going to find the limit of that as n goes to infinity? That looked nearly impossible. So now, instead of having to do that impossible limit, we get to just do this definite integral. The other reason I wanted to point this out is that it shows you where this integral symbol and this dx symbol came from. You might remember from back in section 4.9 that I mentioned that this integral symbol is supposed to look like a stretched out S. That stands for sum or sigma. And that's because it's supposed to symbolically represent this summation sign that we had, where we summed up a discrete number of n different rectangles areas. So in the limit, when we allow the number of rectangles to go to infinity, we get this integral symbol, this stretched out S, that stands for sum, or you can think of it as standing for sigma. And this delta x, remember what happens to our rectangles as the number of rectangles goes to infinity. The delta x, the width of each rectangle, gets smaller and smaller and smaller. The delta x's go towards 0, we said. And in the limit, as you get more and more rectangles, we think of those widths as becoming infinitesimally small, and we represent that with the symbol dx. So this delta x here in the limit becomes a dx symbolically, and this f of xi that's right here becomes f of x. So the definite integral from a to b of f of x dx represents symbolically this idea of doing a sum of a discrete number of n rectangles areas, but it's what happens as you let those number of rectangles go to infinity. Okay, let's go ahead and look at the next page. Okay, well, let's go ahead and do a few examples in which we apply the fundamental theorem of calculus to find the area under a curve, and we'll also use this new notation that we've learned for the definite integral. Okay, so here's an example. Find the exact value of the shaded green area. So we're looking at this patch of green area. We want to find out exactly what that's equal to. Notice that this black curve is the function y equals x squared. So our f of x is the function x squared. And we're finding the area from, well, it looks like this area starts here at x equal -1 and ends here at x equal 2. So we want the area under this curve on the interval from -1 up to +2. And I noticed that y equal x squared, my f of x function, is a continuous function. It's a polynomial. It's definitely continuous everywhere. So in particular, it's continuous on the interval from -1 to 2. And also, it's completely above the x-axis, except right at 0 where it touches the x-axis, but it never goes below the x-axis. So I have a function that is greater than or equal to 0 everywhere on this interval from -1 to 2, and is continuous everywhere on that interval. That means I can go ahead and apply the fundamental theorem of calculus, which we'll just abbreviate FTC. So by the fundamental theorem of calculus, I can go ahead and say, well, I can find the exact area under that curve by doing the definite integral from my a value to my b value of my function dx. Well, what is that for this particular function? Let's see, we're going from a lower limit of -1, that's my a value, so my lower limit on my definite integral is -1, to an upper limit of 2, that's going to be my b value. So I'm doing the definite integral from -1 to +2 of f of x, that's just the function I'm finding the area under, that's x squared dx. Okay, well, what's that equal to? Remember, this is our new symbol for the definite integral, and what it says to do is to start by finding an antiderivative of x squared. Well, I can use the power rule. That would be 1/3 x to the third. And then I draw a vertical line to remind myself that I'm done integrating. I found the antiderivative, but I still need to evaluate at the a and the b value, the lower limit and the upper limit. So I find the antiderivative, draw my vertical line, remind myself I still have to plug in these limits of integration. And we always plug in the upper limit first. So the first thing I'm going to do is evaluate this antiderivative where I replace x with the upper limit of 2. So it would be 1/3 times 2 cubed. And then I subtract the value at the lower limit. So I'm going to evaluate this function where I replace the x with a -1, my lower limit. And then I just evaluate that. So what will that be? Let's see, it looks like it'll be 8/3 minus, -1 cubed is -1, so it's minus a -1/3. So that's 8/3 plus 1/3 would be 9/3, which reduces to 3. And this number 3 is the exact area of this green shaded region here. So that's pretty easy. It's a lot easier than dividing it into n rectangles, figuring out what all those are, and allowing the number of rectangles to go to infinity as we did in 5.1. So that's why I keep saying this fundamental theorem of calculus is like magic. And it's especially like magic to us right now because we haven't even proved it. I haven't even given you an argument for why it's true. That's coming up in just a page or so. Okay, let's do another couple of examples. And here I'd like you to try to use the fundamental theorem of calculus. So try it on example 1 at the top, and also on this second example. Try to find the exact value of the green shaded area. Think about whether the fundamental theorem of calculus applies, and if it does, you can go ahead and find those areas using a definite integral. So pause the video, give them a try. If you get stuck on the first one, go ahead and try the second one anyways, then we'll go ahead and do these two problems together. Okay, well, let's think about the top one. It says find the exact value of this green shaded area here. And notice this is an area under the function y equals cosine x, or you could think of it as f of x equals cosine x. And it looks like we're going from an x value of 0 up to an x value of pi over 2. So it's like half of one of these bumps in the cosine function. We're going to find that area. Well, let's check first and just make sure that the fundamental theorem of calculus actually applies. So that's kind of our question. Does it apply here? Well, for it to apply on this interval from, we're looking at this function, f of x equals cosine x, on the interval from, and our green region starts at a value of 0, that's our a value is 0, and it goes up to a b value of pi over 2. And cosine x is actually continuous everywhere, so in particular it's continuous on this interval from 0 to pi over 2. And also notice that the black curve is above the x-axis. I guess it touches the x-axis right at this endpoint, but it never goes below the x-axis on the particular interval from 0 to pi over 2 that we're considering. So the fundamental theorem does apply for this function on this interval. That means to find the exact area, all I have to do is one of these definite integrals. So I'm going to integrate from my a value, which is 0, to my b value, which is pi over 2. So lower limit of 0, upper limit of pi over 2. My function, little f of x, is the function cosine x dx. So I have to evaluate that definite integral. All right. Well, that means I have to find an antiderivative of cosine x. And the antiderivative of cosine x, the thing I have to differentiate in order to get cosine x, is sine x. And of course, again, I could add on any integration constant, but remember we always choose the constant c equal to 0. So I can just put sine x there. That would be the very simplest of all the antiderivatives of cosine x, where I set c equal to 0. I put my vertical line. That indicates to me that I'm done finding the antiderivative, but reminds me that I'm still going to have to plug in my lower and upper limit. Remember when you plug these in that you always want to evaluate at the upper limit first, then subtract the value of this antiderivative at the lower limit. So I'm going to do sine of pi over 2 minus sine of 0. Okay, well, what are those equal to? Sine of pi over 2 radians would be the same as sine of 90 degrees, and that is equal to 1. I subtract the value of sine of 0 radians, which is the same as 0 degrees. That's a value of 0, and I get 1. So the exact area of this green shaded region is equal to 1, adds up to exactly 1. Okay, let's look at the next example. First, we'll just check that the fundamental theorem of calculus actually applies here. So let's see if it does. We're looking at the function f of x equals 1 over x, which is not continuous everywhere, but what interval are we considering? We're considering just the interval from 1 to 5, because we're only finding the area under the curve starting at an x value of 1 and ending at an x value of 5. Now, if I consider the function 1 over x, it's not continuous everywhere, unlike the cosine function. It's discontinuous. Where is it discontinuous? Well, it's only discontinuous when this denominator is 0. It's a rational function. And this denominator is 0 at x equals 0. But notice that is not in my interval from 1 to 5. This is a nice continuous function on the interval I'm considering. So it's continuous on that interval. Also, the black curve, the 1 over x curve, is above the x-axis everywhere from 1 to 5. It never goes below the x-axis. And so the fundamental theorem does apply. F of x is greater than or equal to 0 on the interval from 1 to 5, and it's continuous on the interval from 1 to 5. That means I get to apply the fundamental theorem. Makes it easy to find the exact area. Let's see, we're doing the definite integral from, and my lower limit, my a value, would be 1. My upper limit, my b value, would be 5. And the function I'm integrating is just the function I want the area underneath of. I don't know if that's very good grammar, but you understand me. So I'm doing the integral from 1 to 5 of 1 over x dx. I go ahead and find an antiderivative. So now I gotta think, what function do I need here so that if I differentiated it, I would get 1 over x. And you remember we did this exact antiderivative back in section 4.9. So we're thinking backwards, and the function that I want to start with, whose derivative would be 1 over x, is the function natural log of absolute value of x. So that would be one antiderivative of 1 over x. Of course, I could add any plus c on there, but again, I choose the very simplest antiderivative. Fundamental theorem of calculus says I just need an antiderivative. Any antiderivative doesn't have to be the set of all antiderivatives. So I just pick one of them. I'll pick ln of absolute value of x plus 0. And I'll draw my vertical line. That means I've found the antiderivative, but reminds me that I still have to plug in the upper and lower limits. Okay, so let me plug in the upper limit, and that would be ln of absolute value of 5. And then I subtract the value of this antiderivative at the lower limit. It's always antiderivative at upper minus antiderivative at lower. It's your capital F of B minus your capital F of A. So natural log of absolute value of 1. And of course, I don't really need the absolute value signs here because 5 is already positive, so absolute value of 5 is 5. And same thing here, this would just be natural log of 1, absolute value of 1 is 1. So I get ln of 5 minus, you might remember that the natural log of 1 is equal to 0. If you draw the natural log function, it crosses the x-axis. This is the natural log of x function. It crosses the x-axis right at x equal 1. So it has this point 1 comma 0 on it. So the natural log of 1 just turns out to be equal to 0. And so I get that the exact area under this curve is whatever natural log of 5 is. And remember, that's just some number, but that is this green area. So natural log of 5 is the area that's shaded in green here. And if you want an approximate value for that, you can always plug into your calculator. I think that I did that, and I got that this is roughly 1.60944379, at least to the accuracy of my calculator. But the exact value is natural log of 5. Okay, great. So now we've done some examples. We can see that it seems really great. Fundamental theorem of calculus, I love it as long as my function is continuous on the interval I'm talking about, which a lot of our functions are, and as long as it's positive or 0, doesn't go below the x-axis on our interval, I am all set, and I know how to find the exact area under the curve. Well, sort of. So that's what I want to talk about on this next page, is this remark. To be able to use the fundamental theorem of calculus, even if f of x meets our requirements, it's continuous on the interval we're talking about, and it's above or on the x-axis on that interval. To be able to find the area under it, we have to be able to find an antiderivative of little f of x. We really haven't encountered any. I haven't given you any functions that you don't know how to find the antiderivative of the function. So let me just give you an example. Here I have this nice curve, f of x equals x over x squared plus 1. It turns out the graph looks something like this. This is a rational function. It's never undefined because the denominator actually is always positive. X squared plus 1 is always a positive value. So it's a rational function, but there are no places where the denominator goes to 0, so it means that it's actually a nice continuous function everywhere. So I'll mention that this function is continuous everywhere. So in particular, it's continuous on the interval that I'm looking at. I have a green shaded area from 0 to 2, so it's definitely continuous from 0 to 2. It's continuous everywhere. And I can see that the graph is always above or on the x-axis on that interval from 0 to 2. So f of x is greater than or equal to 0 on that interval. So it satisfies all the conditions of the fundamental theorem of calculus. So I would normally say, oh, great, now I can find this green shaded area, which is the area under this curve from 0 to 2, just by doing my definite integral. My lower limit, the green area starts at 0, so my lower limit is 0. My upper limit will be 2 because the green area ends at 2. I just pop my function in there. This is my little f of x. And it looks like I'm all set to go. So the fundamental theorem of calculus applies, but now I have to go ahead and think, how do I find the antiderivative of this? There are two terms in the denominator, so unfortunately I can't sort of split it up into two fractions the way we did some of our problems back in the 4.9 section. And actually, this thing, gosh, if you just try to think backwards and think, what function do I need here whose derivative would be x over x squared plus 1, well, you can think about it for a while and you probably won't get the answer. So there's a problem here in the step where we're trying to find the antiderivative and then evaluate that antiderivative from 0 to 2. And unfortunately, this is a function that you don't yet know how to find the antiderivative of. So this is actually something we don't know yet how to find an antiderivative. And in fact, you will learn how to find the antiderivative of this function later in this course. We learn to do it, I believe it's in section 5.5, and you have to use a technique called U substitution, which is a technique for, sort of a trick for integrating that allows us to rewrite this in a form that we do know how to find the antiderivative, and we just don't know how to do it yet. So when we get to section 5.5 and learn this U substitution trick or technique, we will be able to do this problem. But you don't know how to do it yet. So the fundamental theorem at this point in time doesn't actually help you. It helps you with a lot of problems because you know how to find the antiderivative of lots of functions, but you don't know how to find the antiderivative of this one yet. You'll learn how to do it later. Now let's look at this problem. Here I have a shaded area from 0 to 1 under this curve, which is the curve e to the x squared. Well, e to the x is a continuous function, and x squared is a polynomial, so it's a continuous function. So the composition e to the x squared is continuous really everywhere. So in particular, it's continuous on this interval from 0 to 1, and I can see from the picture that the graph is definitely above the x-axis everywhere on the interval from 0 to 1, so it satisfies the conditions of the fundamental theorem of calculus. That means that the exact area of this is given by this definite integral. It would be the integral from my starting point, 0, to my ending point, 1, of this function, e to the x squared dx. But again, we have the problem where we're trying to find an antiderivative of e to the x squared. And we're thinking, okay, I find the antiderivative, whatever that is, the thing I have to differentiate to get e to the x squared, and then I'm going to evaluate that at 0 and at 1, and I'm going to do the value of it at 1 minus the value of it at 0. Well, it turns out not only do you not know yet how to find the antiderivative, if you think you have a guess, go ahead and try it, and I think you'll see rather quickly that you cannot find an antiderivative of this. And it's not just that I haven't taught you the proper technique yet, but you can't actually find an antiderivative in what's called closed form. In other words, you can't come up with a function like we normally would, like maybe you would guess that e to the x squared is the answer. Try it, differentiate it, and you'll find out from the chain rule that you do not get e to the x squared as an answer. So not only do we not know yet how to find the antiderivative, but no one, in other words, it's not possible no one can find an antiderivative in closed form. And by closed form we mean, I'll say, in what's called closed form. And all that means is in a nice, neat function. the way that we're normally used to finding some function that we can actually write the function down, take its derivative, and check that you'd end up getting e to the x squared as an answer. It's just not possible to do it for many, many functions. It doesn't really mean that the fundamental theorem of calculus doesn't apply. It just means that there's no way that we can find this antiderivative, plug in the 1, subtract the value at 0, and get a number for this area. Clearly this area still exists and equals some specific real number, but we can't find it because we have no way of finding the antiderivative of e to the x squared in a closed format. Well, let me make one last remark. In spite of these problems that we talked about up here, there are an infinite number of functions that you can find the antiderivative of. So if I give you any function that you know how to find the antiderivative of, any function f, then you're going to be able to use the fundamental theorem of calculus to find the exact area of this weird shape underneath that curve. So you've gone from being able to find the area of basically 3 shapes. Remember, at the beginning of this section, we decided that the only things we knew how to find the exact area of were rectangles, triangles, and circles, or maybe combinations of those 3. You've gone from being able to find the exact area of 3 shapes to being able to find the area of an infinite number of shapes, and that's really cool. By the way, when you go into second semester calculus, you will learn lots of techniques of integration that will greatly expand the kinds of functions that you can find the antiderivative of, and that means that will expand even further the kinds of things you can find the area of. Okay, let's go ahead and look at the next page.